righty. So one of the things, I'm actually going to jump a little bit ahead. I'm going to go to this slide because I want you to see this part right up here. Very important right there. Okay? All right. Oh, wait. So we want to talk about that right there. Okay? So that is very important. If you don't know that, then you need to get that in your brain and have it like tattooed on the back of your eyelids, and so you see it when you're sleeping, all that fun stuff. Okay? That is extremely important. What this is saying is that if we are in exponential form, y equals b to the x power, that we solve that by changing it to logarithmic form. So that would be x equals log base b of y. Okay? That's what that is saying. If we're in logarithmic form, we switch it to exponential form to solve for whatever we need to solve for. So if we are sitting here, log of x equals -2. First off, if there's no base written, it's assumed that we are log base 10. We're in our common log base. Okay? So this is saying 10 to the -2 power is equal to x. So this one then would be 1/100th. Next one is saying log base 2 of x equals 4. So we switch forms with it. 2 is my base, 4 is my exponent, x is my argument. 2 to the 4th, 16. Try those two. Natural log has a base of e. When we're dealing with bases of e, we just leave it in terms of base of 10, exponent of the 1/2 power, so that is the square root of 10. Questions, comments, concerns, clarifications? Oh, there. Come on back. There we go. Okay. So graphs of logarithms. Okay? Remember that an exponential and a logarithmic are inverse functions. So when we were graphing exponentials, we had horizontal asymptotes. So if we're an inverse function, our domain becomes our range becomes our domain, we flip-flop them. So a logarithmic function is going to have a vertical asymptote. in an exponential function, we had a domain of all real numbers. In a logarithmic function, so the domain becomes my range on the inverse. So then this would be all real numbers. X becomes y, y becomes x. So if we have a horizontal asymptote at y equals 0, that means we're going to have a vertical asymptote at x equals 0. My range was all of the y's greater than 0. So that means my domain is going to be all of the x's greater than 0. So a logarithmic function will not exist on the left half of your graph. It can't exist over there. We had a y-intercept here of I plug in 0 and I get out 1. We can have an x-intercept here of, well, these two are going to flip-flop. So my x-intercept is going to be at 1, 0. Logarithmic function looks like that. Now, if we take the two special bases, base 10 and base E, in the past, so the exponential function would have been y equals 10 to the x power. That's what we would have been. And so now we're inverting that. Okay? So back when we were dealing with exponential functions, we came up with, we said we need to graph 2 points where the exponent is equal to 0 and where the exponent is equal to 1. Well, if the exponent is 0, then that's the point 0, 1. If the exponent is 1, then that's the point 1, 10. Now if I invert that, so now I'm on log base 10 of x, and I want to graph that, the inverted graph point is going to be at the point 1, 0. Because in my brain, I'm thinking to myself, y equals log base 10 of 1. What exponent? Logs are exponent finders. What exponent do I put on 10 to get 1? The answer is 0. So that's why it goes to the point 1, 0. The second point, 1, 10, in my exponential, in the logarithmic function, it would be y equals log base 10 of 10. What exponent do I put on 10 to get 10? 1. So that's why we go through the point 10, 1. When would we hit 2 for a y value? We hit 2 for a y value. So the point something, 2. What do you got? How many just said it? 100 comma 2, yep. Okay, and that's way off that board. So this one would have a vertical asymptote at x equals 0. This way, that way. And then we would have this. Oh, back to me. Take a sharp right turn at Albuquerque. The exponential function associated with this one would be y equals e to the x power. And so if we go with our exponent of 1, instantly regret that. We go with our exponent of 0, e to the 0 power is 1. If we go with an exponent of 1, e to the first power, right? Which is 2.7-ish, right? 2.71828. 9-8, something 8, 4-8, 6-8. Right? If I flip-flop those, now I'm going to go through the point 1, 0, because the two functions here are inverses. Switch the My second point would be 2.71. I would still have a vertical asymptote at x equals 0. At e squared, 2.71 squared, so that would be something like 8.9. Anyways, at like 8 point something, we would finally hit 2. At e cubed, we would hit 3. At e to the 4th power, we hit 4. And so on and so forth. Yes, indeed. Yes, ma'am.
Why would e to the 4th be so long? I thought e is basically 3.71.
Yep. But it's 2.7, so it's almost 3. So it's 3 times 3.
So you said
E to the 4th would be somewhere in the 80, 78 range.
Okay, but I think I heard you.
At e squared, I said.
Oh, okay.
Yeah. Just forgot. Class started 20 minutes ago. Oh, why is okay. Alright. So now let's talk properties of logs. Okay, let's use that. There are 3 very important properties and 1 extremely important formula that you need to know prior to the 12th of October. That's when you're going to get tested on this stuff. Actually, you'll get formative on it this week, and then the test will be on the 12th. Okay? Side note, your Starbucks lab, the green lab that you started yesterday, that is due sometime between now and Friday. So the first are the properties. The first property that we need to talk about is the product rule. The product rule says that if in the argument, side note, inside this set of parentheses on a log, that's called the argument of the log. If you are multiplying something on the argument, you can break that up into two separate logs. So this would become log base b of u plus log base b of v. If you're multiplying three things, you can just keep adding them. Okay? So if it was u times v times w, it would be log base b of u plus log base b of v plus log base b of w. Okay? So it would always, however many things you're multiplying, as long as you are multiplying, you just keep adding in logs. The second rule that we're dealing with is the quotient rule. So now in the argument, if you are dividing two terms or more, okay, then that can be broken out into log base b of u minus log base b of v. And lastly, we have the power rule. And the power rule says that if we have an exponent in the argument, we can take that exponent and we can multiply it out in front of the log. We will use these three rules to expand and condense logs. If we're expanding logs, we're going to take one log and we're going to make it become many logs. If we're condensing, we're going to take many logs and make it become one log. So these rules work in both directions. Now, before we get to that, though, I would like to talk about the uberest of importance, and that is the change of base formula. If you are fortunate enough to have a TI Inspire calculator, they now do this for you on your calculator. If you are still a TI 30X type calculator person, you need this formula. Or if you're in any other style of calculator, you need this formula. And the change of base formula says that if we want to evaluate log base b of u, okay, if u is a power of b, we can do it without a calculator. But if it's not, we need the change of base formula. And that basically says that we take the common log, log base 10 of u, and we divide it by log base 10 of b. If you're not a fan of the common log, then you can use the natural log. You just can't intermix them. So if you're going to go with log base 10, you're going to go log base 10 both in the numerator and the denominator. If you're going to go with natural log, you've got to use natural log. That change of base formula allows any calculator to evaluate a log. Okay? Let's put some of these to work now. So we are going to be expanding here first in the first 4. Okay? So when we are expanding, we're going to take all of the things that are multiplied together. So in my brain here, I'm saying to myself, this is 100 times x times y to the 5th power. So what I do with that then is I say, well, this is log of 100 plus log of x plus log of y to the 5th power. I've taken my single solitary log and I've expanded it, which is what the directions told me to do. Expanding logarithms, products, quotients, and powers. So I've utilized my product property, my product rule. Now I need to say to myself, can anything else be simplified? And the answer is yes. Because 100 is a power, remember our base here is 10. 100 is a power of 10. What power of 10 is it? 2, right? Okay. So log base 10 of 100 is simply 2. Log base 10, or log of x, is just log of x. That one doesn't get simplified. But on the last one, I've got an exponent, so I can put that exponent out in front, and I can go 5 logs of y. Okay. What I'd like you to try now is I'd like you to try the next group. For the second one here, I get 2 natural logs of x minus 3 natural logs of y. Agree? Okay. For the third one, I start out by saying, well, this is log of the cube root of x plus log of y squared, because those are both being multiplied together. Then I'm going to subtract off log of 10, and I'm going to subtract off log of z. Because both of those are being divided. So this becomes 1/3 log of x plus 2 logs of y minus 1 minus log of z. Yes, ma'am.
So even though in the beginning 10 and z are getting multiplied by each other, it stays
because they're both down here,
Okay,
right?
so. it
So
doesn't matter.
technically this would be minus log of 10z, right?
Right,
Okay, which log of 10z then would be minus log of 10 plus log of z, right? But then that negative sign is distributed in.
got it, okay.
Yep.
That's-
Natural log of the square root of x plus 4 minus natural log of z to the fifth. So then this would be 1/2 natural log of the quantity x plus 4. And yes, I would have to put that in parentheses. Minus 5 natural log of z. Questions, comments, concerns? Let's go the other way now. Let's take a long string and let's condense it. Okay. So first thing here, I would apply the power property. So this would become log of x to the 1/2 minus log of y cubed. When we're expanding, we apply the power property last. When we're condensing, we apply the power property first. So then this would become log of the square root of x divided by y cubed. That would be my condensed single solitary. I want one log. You try the next three. You can take it left to right if you want. There's many different ways that you can do this one. Okay? So this is the natural log of 2 divided by x minus the natural log of y cubed. So I've still got to divide by y cubed, which means that it's going to go in the basement.
So why is 2 over x?
Because 2 is what we started with. So if I just look at this one right here, and I apply the quotient property in reverse on it, it would be 2 divided by x. With me? Okay? Then if I take that and I apply the quotient property to this, it would be 2 divided by x divided by y cubed. Which would be 2 divided by x times 1 over y cubed, which is what we got. Okay? Or another way of thinking of it is because this one here is being subtracted, it's got to go on the bottom because of the quotient rule. Okay? Because this one here is being subtracted, it's got to go on the bottom because of the quotient rule. Okay? Right? Yes, ma'am.
So when I did it, I got natural log 2 over x minus 1, or y cubed. So why is it multiplication and not subtraction? I thought it
Because-
is multiplication.
because in our rules, we have no adding and subtracting.
Right, but I thought the subtractions
Make
were
division.
equivalent to division.
Division. So when we're going backwards, if we're subtracting, in order to condense them, we have to divide.
Right, but we're multiplying x by dividing.
Because they're both being subtracted.
Oh.
So another way of, yet a third way of, one too many. Yet a third way of thinking of it is we could have this be natural log of 2 minus the quantity natural log of x plus natural log of y cubed. Okay? And then those two inside the parentheses get combined with multiplication, but then get divided by the 2.
So if we were to add like another subtraction, like another natural log.
After this,
Yeah, like onto the
downstairs.
It would also just go
Yep.
down. Okay.
Yep. Because they're all being subtracted.
Okay.
So here, this one would become the natural log of x to the 5th plus the natural log of y squared minus the natural log of z to the 1/2 power. So the first two get combined with multiplication. And the third one, oops, I put x, should be z. It's downstairs with the rest. I get the log of, on the top, 9 times the cube root of 5x, in the denominator, y to the 4th. Now, if there were a set of parentheses, if we put a set of parentheses right there, then that 9 is downstairs. Without that set of parentheses there, it's upstairs. Okay. Questions, comments, concerns, clarification? Okay. Do a little change of base. Little COB. Okay. So again, this only works, I shouldn't say it works no matter what, but we only really use it if the argument is not a power of our base. So for instance, 8 is not a power of 3. I don't know what exponent I can put on 3 to get 8. Okay? So we use our change of base formula. So that would be here, it would be log of 8 divided by log of 3. Or, if you're a fan of natural logs, it would be the same answer if you went the natural log of 8 divided by the natural log of 3. Natural log of 8 divided by natural log of 3. Oops, where'd my 3 go? 3 went there. And I get 1.89279. Now, logically thinking, exponent on 3 to get 8 needs to be bigger than 1, but smaller than 2, because 3 squared is 9. Closer to 1 or closer to 2? Closer to 2, which we've got 1.89 to it. If we wanted to check it, we could go 3 raised to that power, and we get 8. Okay. So 1.89, usually we will have you round to 3 decimal places. So I would say here 1.89. You use change of base now in a calculator to find me these next two. Log base 4 of 16 and log base 6 of 100. You just add them in. The log base 4 of 16. You don't have the 100. Okay. Because do we need a calculator for log base 4 of 16? No, because what exponent can I put on 4 to get 16? 2. Check it. Check it with a change of base form. .570. Okay, check it, right? Because we want to be on 6, so the exponent of 6 to the answer gives me 100. 2.57. Okay.